So far we've developed Dijkstra's algorithm, which lets us find the shortest path on a graph, on a weighted graph, just like we have here, where each edge has a weight. In this case, I've given them all weight 1. And we did that by keeping track of the cost of the path so far. At each node, we consider what was the cost to get to this node. So for example, Dijkstra's algorithm would consider these two nodes as being equally valid because the cost to get to either one is 1. So just as an example, and once it's gotten that far, it will consider the cost to get to this node as 2, which is good because it's going in our goal direction, but it'll also consider the cost of this node right here as 2, and the cost of traveling this way as 2, even though we know we don't want to go this way. It's completely out of the way. We want to go here on the left. But then if there's a node over here, this is also cost 2. If there's a node over here, this is also cost 2. These are way out of our way. We don't even want to think about these nodes. And so we want to improve on Dijkstra's algorithm, which would consider these nodes. We want some way to get them out of the running. So we're gonna add to this heuristic that we've had so far. I'm going to call this G. Oh my God, that looks really bad. G, and we're going to add some other kind of function to estimate. I'm really trying to write neatly here. The completion cost. So in addition to calculating the cost of the path so far, we're also going to try and estimate the remaining costs that we have to travel. And we're going to see that this is going to improve our algorithm quite a bit. And this has a new name. This is called the A* algorithm. Okay. So then when it comes time for us to calculate the total cost of a node, that total cost is going to be F, and we're just going to do G plus H. That is, we're going to do the cost of the path so far, just like in Dijkstra's algorithm, and then we're going to add to it an estimate for the completion. Now, in Dijkstra's algorithm, we used this as our heap condition. We found the lowest cost of the path so far, but instead, here in A*, we'll still do the heap, so this is a very similar algorithm to Dijkstra's algorithm, but instead we will use F as our heap condition. So how do we estimate the completion cost? That is a very good question. In order to know the actual completion cost, we would have to actually solve the problem that we're trying to solve right now. And that would obviously take a lot of time just to get us back. That would make no sense. So instead, let's just use an estimate. Let's use the Euclidean distance, the geometric distance. And that takes us all the way back to algebra class. So let me draw a little diagram right here. As a quick review, this is our right triangle. And if it has sides A, B, and a hypotenuse C, then Pythagorean Theorem says a squared plus b squared equals c squared. And to find the length from this point to that point, we're going to, solving this equation for c, we're going to find that c is the square root of a squared plus b squared. So very good. So for example, if we want to find this distance right here, from this node to this node, that would make this edge right here A, and this edge right here B, and now you can see that we have a right triangle. And so if this distance is 1 and this distance is 3, then that would be 1 squared plus 3 squared, which is square root of 10. So that's going to be our distance estimate for the completion cost that we're going to use for h. So let's just continue there and pretend that we're using Dijkstra's algorithm. I'm sorry, we're using A star here. A star starts out just like Dijkstra's algorithm does, by looking at both of its neighbors. But now it will calculate g and h. It will say, let's start with this guy. It will say g, the path to get to h, to this node, is going to be 1, and then we'll add to it the estimate completion cost. So let's see, we had 1 plus this that we just calculated using our Pythagorean theorem was square root of 10. So 1 plus square root of 10. Square root of 10 is about 1 plus is about 3.16. So this is about 4.16. Now let's do it for this guy. We want to start here and go here. So the cost of that edge is 1. Then once we're here, we want to know the estimate to get from here to the end. And that looks like 2 to me. We don't have to do any Pythagorean theorem there. It's just 1, 2. So 1 plus 2 is 3. So it looks to me that 3 is less than 4. And so we're going to avoid going over here. We're going to choose this one as our next target. And continuing A star, we do this again. It's really just like Dijkstra, except you do g plus h instead of just g. For Dijkstra, this h guy right here, I couldn't spell his name properly. This h guy right here is always equal to 0. But for us, we're going to calculate both g and h. So if we continue here, we're going to say the path so far is 1, 2. And the estimate to complete is 1 more, it's 3. But if we take a right, then our path is 1, 2, plus this edge, 1, and then plus an additional estimate to get to the goal, which is square root of 2. And I can already tell you that 1 plus 1 plus 1 is going to be less than 1 plus 1 plus 1 plus square root of 2. So then we make a beeline right to our goal, and that's A star. We have avoided completely the entire right side of the graph, which means we get a result much faster with A star than we get for Dijkstra's algorithm. So let's head to the code and see it at work. Because Dijkstra and A star are so similar, all we have to do is rewrite this one little section of our code, and we automatically graduate from Dijkstra to A star. So I filled out this part here. This is the part that Dijkstra uses, and we're going to add the h function for A star. And let's see what that will be. Let's get our test node and find its, that's wrong, test node. There we go, and find its debug position. And unlike our math section, we're not going to use the Pythagorean theorem. This time we're just going to use our good old length function that we wrote before, which actually does use the Pythagorean theorem inside of it. So let's see, now we've calculated g and h. For f, we just add the two together. We add the g weight plus the h weight, and we have the f weight, and we're done. We save that, we run it. We wait a moment for it to compile on my old computer. It's really old. Okay, here we go. Very nice. So I'm going to press G to step through the algorithm. It's the same as Dijkstra. It adds all nodes to the open list. and then it picks the two neighbors and calculates their weights. But this time it sees that this neighbor here on my left is the lowest cost neighbor, and so it continues there, finding more neighbors, and then bam, done. Now let's go back to the algorithm and do it the Dijkstra way by setting this to 0. Remembering that A star and Dijkstra are equivalent, except for this line right here being set to 0. And actually I have to do it in this section of the code as well. So running that, and hopefully it doesn't take as long to compile. Good, it didn't. Now when I run it, you can see that Dijkstra gets sidetracked. It goes to this node on the top right because there's nothing to tell it that the node on my left is closer to the goal. And so it'll eventually get there. They'll both get you the same correct answer, but Dijkstra will just take longer. And to illustrate that point a little bit more, I'm going to come here to this wonderful animation on Wikipedia. You can see Dijkstra filling up the space as I showed you before. And it can take a while to get to the result. There it is. But with A star, you can see it goes. It's still got to get around this this obstruction, but you can see it makes much more of a beeline to the target. Good. So this was the last video on. Well, no, we have one more video. We have a wrap-up video on graph theory coming next week. So I'll see you then.